Okay, since it's 9 a.m., I think I will start. Welcome for this session about supercomputing or monitoring of supercomputing, supercomputers. The agenda reads as follows. First, I will start with a couple of sentences about me, then talk a little bit about the origin of HPC on a few slides, then what we see today, and what are the future challenges in monitoring and maintaining supercomputers. And at the end there is a Q&A, and I hope, since it's a bird of the feather session, that we have an extensive Q&A session, so don't be shy and don't hesitate to ask questions. Yeah. And if there is time at the end, I might can give you a little tool demo of a tool that I will show as well. So my name is Christian Kniep. I work for Bull in R&D for HPC, the HPC software stack. So maybe some of you were attending last year Birds of the Feather session I gave about InfiniBand monitoring. The title was Problems, or InfiniBand Problems, Do You Care? So it was, it came to that I was 2 years involved in maintaining an InfiniBand cluster, a fairly large one with 4,000 nodes. And this leads to an InfiniBand monitoring tool I was writing and involving it to my bachelor thesis. So I presented this and questions which were raised in terms of InfiniBand monitoring last year. And this year I would like to broaden the scope a bit and not only talk about InfiniBand monitoring, but supercomputer monitoring in general and what the pitfalls are and what we might do about it. But first, a little bit about the HPC origins, where we came from. The first supercomputer, or what you could call a supercomputer, is the CDC-6600. It was for his time a very fast supercomputer, outtakes the current IBM in its age by a big factor. Cray took this off and developed the Cray 1, which leads, or this technology architecture leads the next 10 years or 15 years. The vector ruled through the 70s and the early 80s, let's say, and the numeric wind tunnel was built in the early 90s, and so it's not dead yet, let's say. But and there were even, I would say, in parentheses, weirder ideas. So the CM1 was a bit serial computer with over 60,000 processors. So in this stage, it was not clear which technology will lead to the next barrier. The handling. So I'm just reached 30, so I could not say out of my experience, but as far as I talked to people and as far as I understood, it was close to mastering the OS was the thing in this area, because it was a very closed system, so you have to master the operating system because all the bits and pieces underneath are not that obvious to you. And it was also that system experience was the key, let's say. So if you have a system, you work with it for a couple of years, then you had experience in this, and this leads to you become a better system operator or system administrator. And there were no middleware to master because there were no middle to bridge. So there were not the distributed systems where you have many nodes, or it was, as I said, it was a brick, a big piece that you can dig on. It's not that you have a lot of moving pieces. And it was not as widely spread as the supercomputers of today. So if you think of this age, if you were a student, you could consider yourself lucky if your university has a supercomputer like the CDC-6600 or something else. But it was not likely that you might could get your hands on this machine. So the lack of systems were also a big issue. Today we start with the early 80s, a prototype of Intel, the Touchdown Delta in 92 was the first computer built of 32-bit RISC processors, but as I said, it was a prototype. It was the only system built by Intel. And the article of the Popular Science, this one is from March 1992. If you add zeros to the measurements they took for memory and for not teraflop, but today's exaflop, so if you add some zeros to the measurements, it could be placed today. So it's a very nice read. You can find it on Google Books, and it's a nice one. In 1997, the ASCII Red tear down the teraflop barrier with 1.2 teraflop. It was built out of Pentium Pros with 200 megahertz, and this was the first cluster that outperforms the old machines. And another system to mention, I think, not only because it's a very beautiful picture, I think, it's the Mare Nostrum of the Barcelona Supercomputing Center. It's an IBM machine, but it was run with the SUSE Linux, so the first one with real commodity software, let's say. And this is where we are today. So we have commodity architecture. Normally the boxes on the left, which are 1U or 2U systems. And we are mostly on the same hardware stack. Some things might differ between the vendors. For instance, Bull, as my employer, uses sophisticated cooling mechanism with direct liquid cooling, and this is what differs, but the architecture is basically the same. But that's for the history, or the hardware history, let's say. What today is a problem is the complexity. So as we have one big machine in the early days, nowadays we have layers of different layers on top of the hardware. First, we have the BMC or the integrated light out management that enables us to alter or measure informations of the hardware. And of course, we have Linux or some Unix flavor on top of it, and we use interconnect. As I'm used to InfiniBand, I put InfiniBand here, but it could be 10 gig E or proprietary things that came up as well. Then we had some bash script that might use OpenFOAM or some other application to tackle a problem, and this could be orchestrated by a workload manager like Slurm, for instance. And if you are lucky, then your user script will include returns codes or something that you can handle. So if not, then the complexity will even break, I think. So you have to or let's switch to the next slide. Everything is interconnected for sure. So if you have a problem in OpenFOAM and this is included through InfiniBand, then it's not easy, let's say, to handle these problems properly. And like I said last year, InfiniBand problems are mostly in a context, and it's introduced by a certain user script that uses IPv6 or some other problem, some other software layers, and this is hard to tackle if you only look at the InfiniBand side or the InfiniBand logs, and then you have to note down what timestamp you see this error, and then you get down to the other layers, and then you try to extract information which layer in which time has which problems, and then you have to compare it. And this is very, very hard to connect. And if you're an academic side, or then you have maybe more time or more resources to do this. But if you are in the commercial business, I was working for Daimler. They are doing, or the commercial side is mostly doing best effort support, so you can dig into the problem as long as you like, because someone says, okay, we don't see the error for 1 week, so don't care about it now. We will cross the bridge again then when we see it, so to speak. So that's the complexity is a problem. And services as well, so you have many services like NTP service to distribute the timestamp, without which you don't even can compare the different layers, because if one server has the current timestamp and another differs for 30 seconds or 45 seconds or even 4 seconds, it will be close to impossible to connect the dots that you might have on your notepad, because the times are not right and accurate. So this is a big issue. And there are other services as well, LDAP or NFS or yeah, all the services you can count. And they are interconnected, so it's even getting worse, let's say. Complexity grows. And we have so-called standard APIs. IPMI was brought to life in 1999 by Intel, and others have followed. But if you look at the IPMI installation or the implementation of different vendors, and I think one could include Bull too, it differs. So it's not, if you have a heterogeneous cluster, then it's very hard to have a common IPMI access. And SNMP is the same. Various vendors have various implementations of their data structures, and it's hard to have a common sense of handling these errors. And if someone someone decides to change his data structure, then you're screwed too. Dependencies. So if you want to detect an error in your LDAP server by an SNMP trap that relies on the same LDAP server, then you might be screwed, because this couldn't work. So SNMP is in v3. It's called secure because you can use LDAP and you can use sophisticated passwords. But in my experience, it's mostly a simple password that is set, because on the lowest level you won't interconnect to other services to not depend on them if they fail. So if you want to monitor or to supervise the lowest level, then you won't connect the lowest level to higher levels, and this won't be done. So let's have a look at the monitoring. So the current or the earliest versions of those were, I think, query reply structures, where you have one monitoring master. One can call it Nagios here. And you have a different or a variety of nodes with some services. For example, here I have only 3 with 3 services. And one service is in the warning state, the others are fine. And what the Nagios master does, he queries everyone and says, okay, what's your status? And they reply green, except the service 2 or node 1. And you have to ingest or digest every status and filter out this one that has an error. So this is done by Nagios, so you don't have to worry. But if you have a pattern, so let's say this service has a pattern that it raises a bit and then it gets an error, and this is done every couple of minutes or every couple of hours or regularly, then you couldn't know at the second peak that there is a pattern, because you don't get the history of all the values that are introduced by this service. And this was, so here this is a peak. That was handled by Nagios or others to extend the reply to be a little bit richer, let's say, and introduce a very ugly time series database picture. I'm not the artist, sorry. Which will give you the same status, okay, or 1 in this case, and it will enrich us with the values that leads to this, or other values can be included, but let's suppose it's a value that leads to this. And this will be inserted into the time series database. In Nagios' case, it was RD tool. with the timestamp, and therefore you can get a graph plotted out of these values, and you can see that there is a pattern, and a human could easily see this error pattern and say, okay, wait, maybe there is, I saw something in the metrics, let's say. One big issue with Nagios, in my opinion, is, or in my experience, is that the accessibility is quite difficult. If you have 10 nodes or 50 nodes or maybe 100 nodes, might be okay with a couple of services. But if you have, like in our case, 4,000 nodes with, I think in the total about 30,000 services, and there is one error that leads to other errors, then then you could not see this. It's impossible to access this. What we have done, we used a pipe. There is some API that you can query to script Nagios, but it's not commonly, or it's not common use. And we script our way around it to, for instance, if one rack was into maintenance, then we have to set every node to a state, okay, he's in maintenance. And this could be done by mouse, but if there are 40 nodes, 50 nodes, you will do it one time, and then you say, okay, there has to be another way, because it's impossible to do this by mouse. And even if you're having 100 nodes that are in maintenance, then you said, okay, we have to do something. And therefore, a colleague of mine scripted a little tool that that enables you to say, okay, node 100 to 500 are in maintenance now, and therefore it was usable again. But still, the error related to another error is hard to tackle. There is a parent architecture in Nagios, but it has its problems too, I think. And you have also, on the website of Nagios, I found this, so you have also the possibility to get alerts. Usually it's an email, or you can use something else, but problem with these alerts is if there is one alert that is a false positive, you might say, okay, this one is fine. But as you see in the normal case, you have 100 emails that's claiming something is failing, and then the administrator says, okay, after the second or the third email, oh, where's this filter function again? And then everything will be marked as a read and dumped to dev0 and out of null, and then you never see this error again. And this is an issue, let's say. And because it's looked like this, Nagios say, hey, and you say what? And then the Nagios say, okay, this SDA is critical, and you don't care about this SDA, it's 4 a.m., so you won't consider this an issue which causes you to wake up. So the accessibility and the responses that Nagios gives you are not as optimal as it could be. But for the job to be done in this time, it was totally suitable, because what normally would wants, or what the user wants, was having one state or one site he can look at and see that everything is fine. So if you have a small cluster, then you might operate it that you will have, or you want to see everything green, and if it's not green, then you will work as long as it takes to keep it green. So the normal state should be everything is green, and when you have the exception that something is red, then you will work on that. But if you grow to 5,000, 10,000, or what the future will bring, 20,000, or like the first, the top one we saw yesterday, 16,000 nodes, then you could not say everything should be green, because it won't be. It will be an exception, and you will pop up champagne if everything is green in a 60,000 node cluster. So this is the exception and not the rule anymore. So future challenges, or current challenges, one could say. First, it's cats versus cattle. This phrase rings a bell. Somebody? Yes? One? More? Two? So a couple of them. This describes, let's say, for instance, we have a forgotten prototype that became the central infrastructure. Someone scripts fancy login script that everyone uses, and this was done on his working workstation, and everyone uses it, but he doesn't know where it was, and he don't care because it works. But someone said, okay, oh, this workstation, oh, it's from the old colleague that left 2 years ago, we can destroy it. And then the next day, everyone came to work and nothing works. And this is considered a cat, because as he wrote, when he wrote it, it was his pet. He raised it, he nursed it, he fiddled around, and no one else was able or was allowed to touch his cat because it was his. And so it was not replaceable, and he has an emotional attachment, I think, to this machine. And then he forgot about it, and it was there. Or this, you have a log file that grows and grows because you only pipe it and append it to the log, and you saw the next day that it was too big, and they say, okay, what we will do? We will do a loop and wait 1 day, so this is 1 day sleep, 24 hours, and then we remove the log file and everything will be fine. But I think that could cause problems, let's say. This is also considered a cat. It's okay. It's not that it's nursed long because only 4 lines of bash script. I don't think that you have an emotional attachment to this, but yeah, I think in general we could say scripts or services or even hardware. Or no, that's another thing. Or we have a script that reply on a specific format. Let's say we have NFS in a certain format. And we monitor NFS due to the parsing of this log. And then someone decides to change this format, and then our whole logging or monitoring infrastructure of NFS was screwed because this format was changed. And maybe it was some Perl script that someone wrote, which is unreadable after 1 day, and then you could not maintain the script, and this is considered a cat too. And I think if you only have to think 1 minute or 1 second, and you have your own cats that you have in your infrastructure. So services, scripts, whatever, that are not replaceable and that has an emotional attachment to someone, or that, yeah. I think now you know what the cat is. Okay, let's come to the other part. If we have a commodity hardware and we have a deterministic way to install it, or a commodity way to install it, well, it's Bool, yeah? So it's the Bool supercomputing suite. And you have some configuration on top of it that will also have a deterministic way to configure your services and not place a shell script on top of the machine and runs it with this remove mylog aim, but have a Puppet manifest that creates or copies a script and includes it in the cron job, and this might be the way to install it. Because you can now swap out the hardware, pop in another one, and it will be installed in the same fashion as the previous one. So this is considered a herd. It's considered a kettle, and a kettle because it has an ID here and not a name. You don't have a personal emotion when you slaughter it because you want to eat it, or maybe it's old and you say, okay, let's replace it, and this is not cute little cow, it's a little cow. So yeah, you can change and you can replace and you can even scale your herd in terms of getting new cows and put them into your on the grass, and you don't have an emotional attachment to them. So this is considered cattle. And this is a term, herding cats versus herding cattle, and with big clusters, or even with little clusters, but little clusters could be cats, but in big clusters you will fail if you have too much cats, and you should have cattle instead. Okay, so monitoring API, as I talked about the layers, in the future or even today, we need to connect the layers. So if we have these different services and different scripts, we need to have a central monitoring that digests every information and helps it easily accessible. Maybe in the future it will predict on this or apply machine learning or whatever. But first, I think we have to have the data that we can data mine and we can work with. Excuse me. So one of these APIs that is very fruitful and very viral in the community is Graphite. It's a framework to handle metrics, as they call it. So metric is just the key value and a timestamp. So it could be sysload 1 with a value like 2 and the timestamp of the current date. This will be pushed to a metric cache, and there are many ways to push it. Could be a UDP or TCP string or send to a socket, or we will see this. And this metric cache will cache it as it is a cache. So he will populate a hash table which has on one side as the key, and as a value a list of tuples which includes a timestamp and the value. So you have a time series database in the RAM, and if the RAM is too small, or you decide to have a permanent saving or permanent storage, then the metric cache will periodically flash this information to disk using a called Whisper format. So it's using a simple RRD format for this. And the metric cache is all not only to push the metrics to it, because without accessing them it's not of use. So there is a pull mechanism too, so a query mechanism where you can query informations and display them or use them in scripts, or do other stuff with them. So what could be a metric that is pushed to this, or how it's pushed to this, is very simple. You have just echo with a string. So this is the key is test.test1 with a random int number and the current date as a Unix epoch. And this is sent to the port 2003 on the local host. And as you can see, I had a loop that will run to infinity, sleep 5 seconds, and send every 5 seconds a random number to my beloved metric cache. And this could be received as a simple query to the cache, where I just describe, okay, I want this key I just used, and I wanted the last 10 seconds of it, and I wanted to have it as a JSON format, and use some JSON pretty print to show it, and this is what will come back. So it's just there's the 2 points I just inserted, and the description of the key. But okay, command line interfaces are fine, but it's more common to have a UI too. So this is a UI, or this is only the picture that is rendered by the UI that you can easily access. And I will show a demo at the end if there's time, and I think we might have some time. Okay, so we are in monitoring context. So let's have the same service we have before, node 1, service 2, and we don't know what this means. But we have not also metrics in our monitoring infrastructure. We also push events to it. So let's say the job scheduler will push an event when a job starts. He will push an event when a job fails. He will push an event if the return code is something weird. Or every other service could also send events. Then you can overlay the events to the metric and say, okay, here is you see the job start is at the very beginning of this included, or this error error rate that is raised, and this will help you a lot, and this will reduce the time to fix the error not only by the factor of 2, but maybe by the factor of epsilon. Or it's you will be very fast because you can connect the dots. And if this UI, as it is in Graphite, is very easy to handle, then the administrator is able to be very speedy, very fast, and could not only use templates that are foreseen by the developers, to errors that are in the wild, but he can also dive into the monitoring system and browse it himself, which is, I think, the very most, very much better than just have templates that are done in the lab, and you're in the wild that will be completely different to what is in the lab. So it should be very browsable. Okay, so half an hour. Now we come to the Q&A, but I would like to start first with a question from me to you. So what do you use? Who uses just a simply query reply scheme I showed first, so just a Nagios without the performance add-on to just see the green dots and only the green dots? No one? Yeah, kind of. Okay. Okay, that's nice. And the rich reply version where you have a performance, or let's first start maybe with who uses Nagios, let's say. Okay, yeah, that's a smarter question for starters. And so one is using just a simple reply, and the rest of you are using the performance plugin, which stores it in the RRD tool. Yeah? No? Someone else? Well, what do you use?
We use boggling for the performance part. And if we want to, and we connect Ganglia and Nagios so that we monitor the thresholds that come in from Ganglia, and then we can set alerts based on that.
Okay.
We disable the alerts in Nagios itself and just see whatever thresholds we need from Ganglia and use that for pushing all the metrics.
Okay.
Aggregating them.
Okay. And but Ganglia, I'm sorry, is using Postgres or is it using RRD?
It's using RRD. It's using RRD tool, but there's RRD cache inside, so
okay.
It scales. It scales very well. We've in a specific scenario, we've gone to tens of thousands of nodes.
Okay. With a lot of services too, then.
Yes, it saves an RRD per metric per host, so we have a lot of RRD. So you can get a lot of I/O, but you can scale it to tens of thousands of hosts with dozens of metrics per host if you use either TMPFS or now RDKHT, which pretty much makes TMPFS obsolete as a solution for this problem.
But it's not possible to compare different metrics, right?
It's
so
it's inherent for the UI. I mean, you can overlay jobs.
Okay.
And connect it with whatever scheduler you're using, Slam, whatever.
Okay.
And you can compare metrics, you can compare hosts, you can create your custom aggregate hosts and compare those. You can export it to JSON.
Okay.
It integrates with Graphite if you really want to.
Okay, that's what I love.
Graphite is good.
Okay.
But yeah, it covers everything.
Okay, so Ganglia. Something else who one would like to mention? So Ganglia is what I miss here. So Nagios or in Chinga or Chinkan. So Ganglia I should add. And how much layers do you measure? How do you measure everything from the very low-level network traffic to the job scheduler to different events to NFS, whatever? So
we go up to, we use the GPFS, maybe.
okay.
GPFS with CNFS, and we use a cluster of those machines that export the fastest with NFS. So they're like the glue between the JBods and the NFS that they export. So there's a lot, and it's distributed. In some cases, we have a lot of such nodes. So it's very important to us to measure NFS SOPs and compare those with GPFS SOPs, which they don't necessarily translate specifically. There's a lot of caching layers in the middle. So we go out to each one of the nodes. We have a script that just dumps all of the NFS ops that node is doing, NFS client ops. We aggregate that across all the nodes. We have a picture coming down from the hosts themselves, and we have a picture coming from the GPFS nodes, and we can compare and overlay those. It's actually all out of the box, so we don't have to do other work, which is pretty cool. I mean, inside Ganglia, and it's open source. Okay.
Yeah, nice. Nice. Yeah, so Ganglia. But I will show Graphite and I don't know. I think it will outperform, but we'll see. So another question, RD tool at that end. My first Python project or bigger Python project was a tool that includes monitoring of the growth of data in a lot of NFS shares around the data center. So it was, one could say, would be a job for round robin, or no, Robin Hood it was called. So, but this was not able to have the history. So we decided, for whatever reason, to do it ourselves from scratch. I had a little Python script that uses, I think it was du, with a handbrake, so it does not put too much burden on the file system. And it was, so the gathering of the information was quite easy. But I was forced to use a self-made product, which was a transport layer. So it was a cat, let's say. It started like a cat, and I used this. And there I encountered RD tool or let's say the unintuitive pain you have with RD tool. So with RD tool you have time slots where you have to send data, and if you don't send it in the particular time slot, then it will apply some magic and predict different values. So if you have 1, 2, 3 send, and on the time step that is half, you send 3, then it will predict it to some magic that I don't like, or maybe you can turn it off, but in my case it was very ugly. And yeah, this starts as a cute cat, and it evolves to a very ugly pet, because I was the only one that was meant to know it, because I was the only one who developed it, and every once in a while there was a problem because my Postgres database was screwed, or the service was not on. And so it's a couple of years ago, but it's a very painful memory. And 2 years later, there were people coming to me, oh, here's this file system monitoring, this is your fault and you have to do it. So yeah, this was where I encountered RD tool, and maybe I'm influenced by this memory that I dislike RD tool. So maybe, and graphite I think will challenge it, and I think we have 10 minutes at the end that I can show it to you. Yeah, and one thing I really didn't like about RD tool is that once you send a metric, or once you set a value at the timestamp now, then you cannot change the past. So if you have different ways of sources that are throwing to your RD tool server, or your file system where the RD tool RD file is located, then once someone writes the timestamp, then you can change the past. So this is kind of, I think it was kind of ugly. And it's also, maybe Ganglia, I don't know how Ganglia does it, but it's not easy to overlay 2 metrics to 1 file. So what normally is done, or what I've seen, is that if you have 1 rack and you have 10 servers, and every server has a RD file, and you want to aggregate this to an RD file, or you want to aggregate this to a metric for this rack, then there will be a little script that creates a new RD file for the rack. And this houses every metric for this 10 servers and aggregates it in some fashion, and then you have this RD file for the server, for the also servers. And this is kind of not real time, and it's kind of hard. And I don't know, do you know how Ganglia does it with RD cache? Or?
Exactly the way you described.
Okay, so I got you, Ganglia is not good, I think. Yes, no, that's a good one. I like this. I have a second.